Now all that's great, but here's the point. We'd like to come up with a temperature scale that's not based on the freezing or boiling point of any substance. Remember that the Celsius scale is based on the freezing and boiling point of water. And so we'd like a temperature scale that doesn't depend on that. So the second Carnot principle implies something important. It implies that the thermal efficiency of a reversible heat engine, since it's always the same as long as you have the same two thermal sources and sinks, it implies that the thermal efficiency of a reversible heat engine depends only on the temperature of the source and sink that you're using. In other words, it's some function of the temperature of the source and sink. What does that temperature look like? Is it like the natural logarithm of the sum of the temperatures? Is it some polynomial expression? Maybe second, third, first order. Here's a first order. What does it look like? Well, it's neither of these. We have to consider a little bit deeper in order to derive it and understand it. Remember that the thermal efficiency of any heat using engine to produce work is 1 minus QL over QH, and that holds for reversible heat engines as well. In that case, it's not the one that is a function of the temperatures, right? It must be the heat flow ratio, Q over QL, that is some function of TH and TL. To figure out what that function looks like, we're going to consider three reversible heat engines. So we've got the same thermal energy reservoir, high and low, but we've got one heat engine on the right, heat engine C, and two on the left. Now on the right hand side, the thermal efficiency of this reversible heat engine will just be 1 minus Q3 over Q1, where Q3 and Q1 are the two heat flows across that heat engine. On the left-hand side, we're going to put two heat engines in series with one another. Heat engine A and heat engine B, both being still reversible heat engines. And the waste heat from heat engine A is going to drive heat engine B. It's going to be the thermal energy source for heat engine B. Now, understanding, of course, there must be some intermediate temperature between T1 and T3, which is at the interface between those two heat engines. So the thermal efficiency of heat engine A must be 1 minus the ratio of the heat flows across that heat engine, Q2 and Q1. Similar argument for heat engine B. Now understand, if we put in the same amount of energy to these two heat engines on the right side and on the left hand side, we must throw away the same amount, Q3, below, because these are reversible things, right? They have the same efficiency. You can neglect the fact that we've got two heat engines on the left-hand side, consider those just squashed down in one thing, and we've got the same thing on the right as we have on the left, right? We've got heat engines that are reversible that produce the same amount of work. In other words, WA plus WB must be equal to WC, and the heat flows must be the same ultimately all around. In other words, the Q1s are the same and the Q3s are the same magnitudes. So thinking of what we thought of before, it's the ratio of the heat flows that must be some function of the temperatures across each heat engine. Notice on the right hand side we've got a function of T1 and T3 because those are the only temperatures that heat engine C experiences. On the left hand side, thermal engine A only experiences T1 and T2, and thermal engine B only experiences T2 and T3. So the ratio of the heat flows across those engines must be some function of the temperatures that those heat engines experience. Now just copying what we had on the last slide to this slide, not changing anything, needed some more space, so we just kind of compacted it a little bit. This is what we've got. Now it's just a mathematical fact. Forget all the thermo stuff for just a second. It's just a mathematical fact that Q3 over Q1 as a fraction would be equal to Q2 over Q1 times Q3 over Q2. I mean, the Q2s cancel. You know that's just math, right? But since the ratio of the heat flows must be some function of the temperatures across the heat engines, we can also write from this equation Q3 over Q1, replace it by whatever that function is of T1, T3. Q2 over Q1 can be replaced by the function of T1, T2, and Q3 over Q2 at the end of the equation can be replaced by the function of T3 and T2 from our heat engine setup. Now this is actually quite interesting because what do you notice here? Well, you should notice that the left-hand side is some unknown function of T1 and T3. Okay, whatever it looks like, we don't know. We're trying to figure that out. But on the right-hand side, we have two separate functions who independently depend only on T1, T2 and T2, T3. But when we multiply them together, the temperature dependence on T2 must go away. I mean, to be consistent, the form of all these functions must be exactly the same, right? I mean, we're just talking about heat engines. So the functional form has to be identical for all three of these functions f on the right-hand side. Now, what functions would work this way? Well, let's take a cue from our fractions up above and say, well, maybe the functional form of the two temperatures is some separate function of the temperatures independently, because if that was the case, well then the function f of T2, T3 would be some other function of a ratio of functions that depend only on the two temperatures involved in it. And this would be consistent because, look, plugging those in, those g functions in, g of T2 cancels in the numerator and denominator and would give us the right functional form for the left-hand side function. It would all be nicely consistent. Okay. So that looks nice, it looks promising if we just break up the dependence to numerator and denominator. But the simplest function g would just be the temperature T. If that's the case, then the ratio of the heat flows for a reversible heat engine, because remember that's what we've been dealing with so far, must be TL over TH, where the temperatures are just the absolute temperatures. Okay? That would be the simplest form. So here's the big trumpet blare. I know we've talked about a lot of things and it seems theoretical, and where are we getting all this from? I mean, all these seem kind of reasonable but pretty clever, and I would say devilishly clever insights. Here's the point. The thermal efficiency of a reversible heat engine is 1 minus TL over TH. In other words, the thermal efficiency of every reversible heat engine out there that would theoretically be in any way possible, even if it takes forever to run it, would simply be 1 minus the temperature of the low temperature reservoir over the temperature of the high temperature reservoir in absolute units. This is a huge thing. This is really important. You might look at it and say, well, you got the trumpet blare there, but who cares? I mean, it seems kind of anticlimactic, right? I mean, it's the 1 minus the ratio of the temperatures. Okay, what can we do with that? Well, think about this. What is the thermal energy source in your car? Well, it's basically the hot gases after the gasoline's been burned, right? That's the thermal energy reservoir, if you will, or that's where the high quality, high temperature thermal energy exists in your car. What about the low temperature reservoir? What's that? Well, ultimately those gases get tossed out the tailpipe. The reason they want to move in that direction, the reason your engine goes forward, is because, well, it's because entropy is being generated. But that aside, it's just the engine's pushing it out, right? I mean, the gases are expanding, and so one piston that's being pushed down is pushing exhaust gases out the tailpipe. So ultimately those gases go to the local atmosphere, right? And there's our low temperature reservoir. It's just the low temperature atmosphere. So what are these temperatures? Well, you know, approximate temperatures might be on the order of thousands of degrees for the gases above the piston, and just, you know, roughly local atmospheric temperature 72 degrees or so, or maybe even in the winter 30 degrees. Your car runs fine in the winter most likely. So those are the temperatures, but we can't just plug those two temperatures in, although we have appropriately identified the temperatures of the source and the sink. We got to plug them in absolute units, right? So the best your car could ever accomplish, let's do a calculation just for fun, okay? We need absolute temperature units. So let's just say that, I don't know, I'm guessing, let's say that the temperature of the gases above the piston in your car is 1500 degrees, so if we have to add 460 to it, let's just round that off to about 2000 Rankine. So TH is 2000 Rankine. What would be the temperature of the local atmosphere? Again, let's make our lives easy. Let's say it's 40 degrees outside, so plus 460, that's about 500 Rankine. So what would be the maximum efficiency you could ever hope to achieve in your car, since it's working between those two thermal energy sources? Okay, so TL 500 Rankine, TH 2000 Rankine. If I take the ratio and 1 minus that ratio, I get 75%. That means the best your car could ever do, operating with an engine that's completely reversible, that would literally take forever to run, would be 75%. that's the best. There's no way to make a car. You can't expect for Detroit or Japan or Germany or any of these places that make engines to make an engine that is more than 75% efficient if it's working between 2,000 degrees and 500 degrees, and saying degrees is not appropriate, but 2,000 Rankine and 500 Rankine. Simply impossible. Because the only way for it to be possible is for us to be able to make some device that moves thermal energy from a low temperature reservoir to a high temperature reservoir without any work input, okay? Which you should believe by this point is not possible. So this is it. This is the limit. This is what we were looking for. If we had a fully reversible heat engine, this would be its efficiency, okay? And it's not because of friction that it is not more efficient. It's not because of friction that it can't achieve 100% efficiency. It's because thermal energy by its nature cannot be converted completely into work. Notice that I was very careful here and I plugged in absolute units. If you find yourself plugging in Celsius here or Fahrenheit or any other relative temperature scale, you won't get the right answer. You might want to make a note of this. It's in the back of this chapter. It's probably the most important equation in the chapter. I would highlight it and I would make a big note to myself, only use Rankine and Kelvin. Okay? Do yourself a favor. Do that and you'll probably save yourself about 20 points on the next test. So the maximum efficiency we could ever hope to get, say, of a engine operating between 300 and 1,000 Kelvin, well, let's see, that'd be 1 minus TL over TH, so 1 minus 300 over 1,000, that's 70%, right? A reversible heat engine would be able to achieve a 70% efficiency. In fact, any reversible heat engine would produce that efficiency. Irreversible heat engines will produce a lower efficiency, 45% if we're lucky. It would be impossible to make a heat engine that's more efficient than that working between these two thermal energy reservoirs. Now you might look at that and say, well, you know, this is a real downer. I don't like this. Because it sounds like that what you just said is that, you know, going back to our gasoline engine, 75% efficiency, the best I can ever hope for is to buy $1 worth of gas and 75 cents push me down the road and the other 25% has to be thrown away. I don't like that. I don't want to hear about this 25% that has to be thrown away. Yes, but hopefully this is giving you some ideas beyond just eliminate all the friction. It's a good idea to reduce friction, but you need to reduce other irreversibilities in the piston as well. For example, does the piston expand the gases very fast? Yes, it does. Now, it's kind of a relative thing because really we're talking about the speed of the piston versus the speed of the molecules bouncing around. And really the molecules do move quite a lot faster than the piston does. But did you know there was a ship, and I wish I could find it, I read about it, I think it was built in the 1800s, and they had pistons on this ship that were absolutely huge. They were so large that they could put chairs and tables on them, and they moved so slowly, people could have dinner on these chairs or on these pistons. And it was just a steamship, and the idea was that you have these massive pistons, but a steamship that's extremely efficient because of the very slow expansion of the steam. And so this, of course, was not very practical. I don't think the steamship lasted very long. I wish I could remember the name of it. But, and you know, I honestly don't know that it was built. Maybe it was a conceptual thing someone had written about. But I understand the idea, which is to eliminate an irreversibility of fast expansion or compression of a gas. It is a good idea in the sense that it eliminates another irreversibility other than simply friction. But what could we do? Well, let's eliminate friction. Let's make sure the piston's not moving too fast up and down in the cylinder if we want a highly efficient system. What else could we do? Well, what if we could make the engine out of some materials that could withstand extremely high temperatures, higher temperatures than we experience in our car's engines right now? That would be a good idea. What if we could make an engine where there's less loss of energy? Because think about it. If we've got, you know, a gas that's at a couple thousand degrees maybe, and an engine block at 200 degrees, you know, if we let that 1,000 degree or a couple thousand degree gas interact with the cylinders of that engine for too long, we're not going to have an engine anymore. We're going to have a pile of molten metal, right? So if we could find materials that could withstand higher temperatures, maybe we could increase TH. and in so doing increase the theoretical maximum efficiency of the engine, and therefore make a higher efficiency engine. Maybe there's a way to lower TL. Now, if we're going to use the surrounding air and surrounding environment as our low temperature reservoir for throwing away waste thermal energy, then probably we're not going to be able to do much about that. But we've already got a couple of ideas beyond just eliminate all friction, right? Slow the piston down maybe, and maybe find materials that can withstand higher temperatures. These are good ideas for increasing the efficiency of our work-producing devices. Here's some calculations of the maximum percentage of energy that can be extracted as work if we vary the temperature of the high temperature reservoir from 350 Kelvin up to 925. There's the maximum theoretical efficiency. And this gives us the idea that thermal energy has a quality to it, or a usefulness to it. Not equality, but quality. And as the temperature of the thermal energy goes up, the usefulness or the quality of that thermal energy goes up as well. For refrigerators and heat pumps, considering a Carnot refrigerator or heat pump, in other words, a reversible heat pump or refrigerator, we can play the same game where QH over QL equals TH over TL, make the substitution in our coefficient of performance equations, and find the maximum coefficients of performance. In other words, if you work for Trane or Carrier or any of those big companies, and you're trying to figure out what's the best refrigerator or heat pump I can make, well, here's the equation for the best refrigerator. It depends on the temperatures, right, that you're trying to work between. The larger the difference between the temperature where you're trying to, take thermal energy out of the refrigerator and move it into the kitchen air, the larger the difference in the temperatures between those two, the worse the coefficient of performance is going to be. In other words, it's a bad idea to take your refrigerator and install it in your house with a hole in the house where the door to the refrigerator opens to the inside, and the heat exchanger for the refrigerator exchanges his heat with the outside. At least in summertime that's a bad idea, because the outdoor temperature in the summertime will be very high. Now, you could make a case to say maybe that's more efficient than your air conditioner then pumping out the waste heat from the refrigerator, but hopefully you get the idea that the higher the temperature between the low and high temperature reservoirs, the worse or the lower coefficient of performance that is achievable. We can do the same thing for heat pumps and find the limit of the coefficient of performance for a heat pump by substituting QL over QH for TL over TH. So these are reversible, in other words, Carnot refrigerators and heat pumps. Now, if you go through the math and you do some calculations with a cool space at 275 and a warm space at 300 Kelvin and consider a refrigerator's maximum efficiency, you should do it. Go to the equation in the back of the chapter. You should mark these as well that I just had on the last slide, and verify that the maximum coefficient of performance for a refrigerator operating between these two limits is 11 or so. It's an irreversible refrigerator would have a lower coefficient of performance, maybe 7 or so. It would be impossible to make a refrigerator with a higher coefficient of performance. And a similar thing for heat pumps. Now, with a heat pump, you may know that heat pumps are not typically all that popular. The reason is because engineers understand this, and so if you make a heat pump, you really don't want to take the air that you're blowing throughout the house up to too high a temperature. I mean, if it's 30 degrees outside and you're trying to maintain a home at, say, 75 degrees in the wintertime or when it's cool outside, you don't want to take the air up to 200 degrees or something, because the maximum theoretical efficiency will be capped so much by that high temperature. Rather, you'd like to take the air to, say, 90 degrees or so, or maybe 80 degrees if the set point is 75. And what ends up happening is the air coming out of the register doesn't feel all that warm to the occupants, and so that's where heat pumps got a bad reputation initially when they were introduced, because the air coming out of the register felt kind of cold. As a matter of fact, if you put your hands over it, it does feel cold, because you would have water on the surface of your skin, and that water would be evaporated off and feel like it's actually cold air coming out of it, when in fact it's warmer than the average temperature of the home. And the purpose, of course, for having that just mediocre warm temperature air coming out of the register is so that you're working between a smaller temperature range and therefore have higher efficiency, which is the whole point of having a heat pump in the first place.